Hello everyone, it is my great pleasure to introduce the physics-based deep learning book, or in short, PBDL. My name is Niels Thüre. I'm from the Technical University of Munich, and this is a project that has been in the works for quite a while that we finally can unveil here. Yeah, by book we of course don't mean a big pile of printed paper, but rather this is a collection of digital resources with the aim to introduce how to couple physical simulations and deep learning, and to give a comprehensive overview of how to best combine these two worlds. Another really important point for us was that there are code examples for all the topics, or the main topics. There are a few Outlook topics without, but you can run this in the form of Jupyter notebooks on the spot to directly, practically get started with these topics. And we're covering a wide range of topics, starting with supervised learning, going to soft constraints, and then really to a tight coupling of physical simulations and deep learning, and then also to topics like reinforcement learning and uncertainty modeling. So a wide range. We won't go into enormous detail for each of these, but the focus really lies on the coupling with the physical simulations. Yeah, let's look at this a bit more broadly. I think we're really living in exciting times. At the moment, we have enormous challenges for humanity. We have climate change, sustainable developments, epidemics, and I believe that deep learning really has a fundamental potential here to change how we can deal with these topics, how we can run computer simulations. And computer simulations really can deal with pretty much anything these days, starting with our bodies, the fluids moving around there, to manufacturing processes, to our weather, to the formation of galaxies on gigantic scales. And one of the core topics in the book is that for all these powerful simulations that we already have, we actually don't want to throw away all this expertise, but we want to keep the numerical methods that we have, and also the powerful physical models that we already have, that we as humans have developed over the last centuries really. But we want to bring in these very powerful and new deep learning methods. So the goal of this book is to introduce how to work in this intersection of the three topics. Yeah, and when talking about this, there's also directly a worry that I want to address. Talking to some people, you still hear, well, aren't these neural networks a kind of black box? Isn't it a bit like magic? What's happening here? These people have some problems trusting these methods, right? Might appear a bit like voodoo to these. And I actually want to reassure that this is completely unfounded, and actually strongly argue against this. I think there's no foundation for this viewpoint. If you think about what happened in the past to numerical methods, they also were not trusted in the beginning. People were worried about numerical problems, inaccuracies, and instabilities, and sure, it was not easy, but they were worked out. By now, they're ubiquitous, and numerical methods are widely accepted and extremely powerful. Deep learning methods are not yet there. There is work to do, but it would have been a huge pity if we had not looked at numerical methods in the 50s. So also, just because all these details are not yet worked out, that's really no reason to not look at deep learning. Hence, I think it's an extremely powerful method. It's worth looking at right now, and these worries are completely unfounded. Hopefully, our book will help to actually provide a starting point and to get into the topic. I directly want to thank a lot of people that have worked on this. It's definitely a living document with a lot of people contributing. We'll keep on working on this. We have a lot of new ideas for additional chapters, more complex topics, and supporting materials. So a lot coming up, but it's online right now. You can take a look if you want at the spot. You can find the link here. I want to continue a bit and now introduce some of the topics in a bit more detail that we deal with in the book. Yeah, so one of the central themes is that using physics is a great idea and an obvious one, but it's not just about kind of patching on a few residual terms or so, but the goal should be to integrate deep learning on par with simulations and tightly bring the two together. And one very good topic to study this is actually Burger's equation. That's used quite a bit in the book. Very simple PDE. You can already see it here on the slide. We have an advection term, a diffusion term. It gives some interesting shock formations. Here we're starting with the blue initial shape, and then that's developing towards the shock in the middle as a very small test case. And being so nice to study and actually kind of a stepping stone towards Navier-Stokes, this is also a topic of quite a few of the examples in the book, and I try to want to show that here. So we have a Jupyter notebook for this, and this is already one that uses a differentiable physics approach. For all of these examples in the book, you can actually find these run and collab links here. This is where I'm at the moment. So just click on it and get started experimenting with it on the spot. I already have this up and running here, and typically there's a bit of a installation startup phase in this first cell here. Here we're actually allocating one centered velocity grid for a 1D burgers simulation. This one doesn't do so much, but here, for example, we're checking what kind of type we have, and in this case, it's already running. The simulation itself is already running in TensorFlow, as you can see here. And potentially, the first interesting step is here we're actually running the simulation in this code block. This is the diffusion step. And here we are executing a semi-Lagrangian step of the Phiflow framework that's used quite a bit in these examples. And then we're computing an L2 loss here for one of the solutions over time. And with Phiflow's record gradients function here, we're getting the actual gradient out of it. So this runs on the spot, no matter what your hardware is in Colab. And here we're not just computing a loss, but from this we could now run some first order optimization schemes, couple these gradients with deep learning and so on. But in this notebook, that's just an introductory model. And if you're interested, I'll leave it to you to actually run an experiment with the whole notebook here. I want to switch back to my slides where I already have the results, because one of the points here is this nicely illustrates the difference between some physics-informed residuals and kind of proper differentiable physics integration. So this is actually what you get in the middle here out of a physics-informed loss. This is now actually visualization over time of the whole burger simulation. Goes towards the direction of the solution on the top. But if we directly bring in the solver, in this case we can actually get very close to the reference, and typically also faster than with this physics-informed loss. So on the right you can see the differences to the top, the error, and as you can see in the lower picture on the right, for the DP, differential physics approach, the error is much lower than for the physics-informed one. That's really just a toy example. There's a variety of more complex cases in the book, and I want to just briefly show some of them. There's one case that uses a full incompressible Navier-Stokes solver to train a neural network, a bit like what I already alluded to before, that really interacts with the simulation. So the goal here is a hybrid simulator that combines neural network and regular solver topics. And as an outlook, also in the book we go into much more detail, but it's super important here that you have a network that really at training time sees this simulation environment, the world it's interacting with, and hence that you run the training with the solver in the loop. And this is the corresponding notebook for that case. This is now a more complex one, and a longer one, which I now on the spot don't want to fully run here. Again, please give it a try. If you want to take a look, you can do that here for the within Colab. For these complex or more complex notebooks, typical structure is that we download some training data. The notebooks typically don't deal with a data generation phase so much. We want to focus on the learning aspect. And now here we set up some our simulation environment. Very important, a random seed of 42 as a magic number, of course. And then we continue here with the simulation setup. And now here we, for example, define the simulation step within Phiflow. This runs a full Navier-Stokes solve now with a current projection step for the pressure here at the bottom. And all this is directly differentiable, and you can integrate it into a deep learning pipeline on the spot. This is also done in this notebook. Here we're setting some neural networks here, typically using a very simple one. As an alternative, you could try a more complex version. There's some interface code here, and data handling in practice also important. But what I want to skip ahead to now is there is the actual training step that is now run in the neural network optimization. And with all this setup, this is now in a way surprisingly easy. We're again training for a time evolution of the solver. So we have these multiple steps that are executed here. We have the simulator from above. That's the Navier-Stokes solve that now runs on a given tensor, typically already in a batch form. And then afterwards here we are actually evaluating the neural network model that received the current state of the solver, modifies that state, and then this is iterated such that the network really sees what's happening and how the changes done to the simulation state affect the future evolution and the errors. And if you continue here, you can see how that works. Again, I don't want to run the full one. This is a bit more complex, but just to preview here a few examples. On the left, again, is a pure solver, then the kind of basic solver that the network interacts with, and on the right side, this learned version. And especially if we can look at the errors of the two, so the left is the original one, and the right side here is the learned augmented solver, this hybrid, and the right side, the error is much lower. So depending on your setup, you can also compute that over time, and you can really, in this way, get a numerical solver that has improved behavior, in this case, for example, lower errors, or that might model some of the terms that are not directly included in your PDE description. So this is a very powerful setup, and in the book we show how to set it up and how to run it on the spot with some examples. Another topic that we deal with that's interesting is reinforcement learning. I'm sure you heard about this in other contexts before, and here it's interesting to consider that for controlling a physical system. What we're doing with this physical system now is that, in a way, we have a model-based approach. That means we actually don't treat this environment as a black box that we just tap around in blindly, which is actually what typically reinforcement learning approaches do. And rather, we are integrating our physical knowledge here again, and in a way, no surprise, but that improves the learning process. Let me show you the corresponding notebook. So here is the version from the book. Again, you can run it on the spot in Colab. This is now one example that uses a few more underlying codes. It's using stable baselines gym to run a approximate policy optimization, and again uses Phiflow and some additional helper codes. You can imagine this is now a more complex setup. It actually also directly runs a comparison between the two later on, and some data generation steps, and then later on the actual physics training part in the gym. Feel free to take a closer look if you're interested in this topic. I want to skip ahead to the results a bit, and if you compare the two approaches now, one classic reinforcement learning approach and one that integrates the physical system, then you'll see that in terms of the forces that are necessary to reach a desired state, so the forces here are the actions of the network, they're mostly on par. The physics approach is actually slightly better, but there's a huge difference in runtime. So the reinforcement learning approach, due to its tapping around in the dark, takes more than half a day. The physics-based one, less than 1/10 of this, while achieving a certain or a similar level of required forces for the interaction. So I think this is a nice example of how much domain knowledge can actually bring for deep learning runs in practice. And as a last example, what's also a really interesting topic in the field is uncertainty. So one way to target this with deep neural networks is to actually use Bayesian neural networks and to do what's called typically posterior inference. So we're trying to learn the full distribution of some unknown target function, which in our case is typically the manifold of possible or admissible solutions given a certain input. There's often a null space, a nonlinear null space, if you want, that means there's uncertainty with respect to the solution we'd like to get out in a physical system. And now the goal here is to actually ideally learn the full distribution of these possible solutions. A nice result of that is, if we run this case, we actually have a network that again deals with the whole distribution of networks that we can sample to produce different outputs. And the notebook for this case does exactly that. So here we're dealing with a Reynolds average Navier-Stokes flow that is now using Bayesian neural nets to learn the distribution of the outputs. This then proceeds by getting a data set, a larger one. This would definitely be beyond the scope of the notebook to set that up. And there's actually a simpler regular supervised case for these airfoils in the book as well. And this is what the data typically looks like. We have a certain airfoil shape that's embedded in a regular grid here, and then we're interested in pressure and velocities around this airfoil given certain flow conditions. And for the network, we can now set up a UNet that uses TensorFlow probabilities flip-out layers. So here's a 2D convolution with this flip-out functionality for the Bayesian modeling. So now for every one of the weights, we're actually typically learning a mean, which is a normal network, plus a standard deviation, such that we can later on sample the distribution of the network and realize this posterior inference case. Again, this full network takes a bit longer to run, which I don't want to repeat here on the spot. But if you're interested, give it a try. This is the training loop, which in this case doesn't look so different from a normal supervised training. Let me directly show some of the results. So once you have this trained, you can do exactly what's mentioned here and sample different outputs. Here's one target airfoil, some given conditions, and then 5 different predictions. And having that, we can also compute the mean of these predictions and then measure the standard deviation of the output. So this is a direct way to estimate the uncertainty of the network. And you can see some examples of that on the right-hand side here. So the first column being the input shapes, then these mean predictions and the standard deviation on the right-hand side. And as you can see, especially around the airfoils, the network is uncertain here. This is a quantity that is normally very difficult to get out of a regular training run, and with these Bayesian neural networks, it gives us tools to actually learn and represent these uncertainties. However, of course, complicating the training. So this does come at a certain cost, but very interesting topic in the deep learning field. If you're interested, please check out the corresponding chapter in the book. Worth noting, this does not yet use this differentiable physics solver, but given the materials in the book, it's in a way a relatively natural combination to go ahead and combine these for further experiments. Yeah, with that, I want to come to a conclusion of this introduction. Essentially, there's a lot coming up in the current state already. The core, the motivation for this book is actually to introduce deep learning as a powerful tool for ultimately all computer-based tasks, but especially for computer-based physical simulations. Another important point that hopefully will be clear after reading and working through it: there's no magic involved. It's the most powerful tool we have for nonlinear regressions, for working with nonlinear functions and optimization problems, but no magic. It's just another numerical method, very powerful one that is. The topic actually nicely fits into the larger scope of differentiable programming. It's probably where a lot of computer-based codes will develop towards in the future. ultimately, right, there's no reason not to interface with these deep learning algorithms. Having simulations or all kinds of other components interface smoothly is a very good long-term goal and also an important one for simulations. So the PBDL book should provide as painless as possible starting point into this topic, and all along the way, or in the later chapters especially, also introduce some advanced topics that are not that accessible on the spot. And especially on the advanced side, we actually have a few very interesting ones coming up. It's also worth directly mentioning this simulation framework that is used a lot for the examples in the book, these differentiable solvers called Phiflow. We just released the version 2 with some neat functionalities. Especially named dimensions are worth noting here, so that gets rid of most of the reshaping code that you might have in some older ones. The simulations basically know about spatial and additional batch and channel dimensions and directly match the required ones. It also abstracts deep learning APIs. You can run it on TensorFlow, PyTorch, or even JAX on the spot, and also the JIT compilation is done, is abstracted in this way. So also worth a look if you want to delve deeper. The book is actually also a very good starting point for getting into Phiflow, and I can directly show some of the example simulations that you can realize with Phiflow. So here's a small 2D simulation, and on the right here a nice 3D one, just as a preview of some examples that are achievable with Phiflow. Yeah, but with that I want to come back to the book. Please check it out. This is the first version. We're happy to see it online. If you find any typos or mistakes, please let us know. Also, if you have other suggestions, we'd be happy to hear from you. And so far, thanks for listening. Stay tuned for further updates.